Hello, I'm a little bit unhappy right now because I just recorded the first 3 questions and then my screen recording stopped for no apparent reason, and now I have to go back and redo everything. So let's go. This is exam 1 from fall 2018 for Calc 3. Okay, we want a line that passes through these 2 points, and we are looking for the intersection point of that line with the xy plane. So all we need for this parametrization is a point that's on the line and a position vector that points or that goes from our first point that we know that's on the line to our second. So let's write that out. We know that 1, -2, 1 is on the line, and for every unit t, we want to move this vector here that we're talking about. And in this case, the vector that points from A to B is going to be 1, 5, -2. And let's see, we're looking for the intersection point of this line with the xy plane. Well, we intersect the xy plane when z is equal to 0. So in order to figure out what value t we need in here, we're going to solve the equation 1 plus -2t is equal to 0, just pulling out the z components over here. So we solve this and we see that t has to be equal to 1/2, which is perfect. We can stick a 1/2 in here. And all we're doing is adding now, and we will have our intersection point. We see that our intersection point is equal to 3/2, 1/2, and 0, which is E. Let's see, we're given 2 planes, and we're asked to find the parametric equations of the line of intersection of these 2 planes. So let's hope my drawing is better than the last one that I made, the one that got deleted somehow. So if we have 2 arbitrary planes and they're intersecting like this, we're going to have 2 normal vectors, one for each plane. And I hope you can kind of see graphically here how if we take the cross product of these normal vectors, we will end up with something that's normal to both, which ends up being parallel to this line of intersection. And since we know that planes are defined, or the coefficients of the planes define the normal vector of that plane, we can just pull out our normal vectors as 1, 1, 1 and 1, -2, 2, and cross these guys. We'll get 4 and -1 and -3. So that automatically gets rid of C and D, and then all we need to do is see for t equals 0 if these expressions satisfy the equations of the plane. So when t is equal to 0, our A is going to essentially be, our x, y, and z coordinates will be 2, 1, 0. For B, we will have 2, -1, 0, and for E, we'll have 2, 2, 0. Plugging these in for x plus y plus z equals 1, we see that A does not work because 3 is not equal to 1. We see that E does not work because 4 is not equal to 1. And for B, for our first equation up here, we will get 2 minus 1 equals 1, which is true. And over here, we will get 4 equals 4, which I'm pretty sure is true. So B is our correct answer. Okay, we're trying to identify a quadratic surface in 3D, and we know for this kind of just classifying our shape, we're not finding any traces or intersections or anything. We don't care about coefficients at all. That's just going to kind of transform how our the overall. So it might take an elliptic cone that looks like this, and our coefficients might widen it out or make it more narrow, but we really don't care because they're all still elliptic cones. So for this case, we can rewrite this as x squared minus y squared plus z squared equals -1, and we know that this will be the same class of quadratic surface. And you might be able to already recognize that we're dealing with a hyperboloid of 2 sheets, because this is an expression, this side of our equation is saying that we're dealing with a hyperboloid of 1 sheet and then over here on the right with a negative waist size. So that's going to give us our classic hyperboloid of two sheets. And if you want for yourself, you can go rearrange this equation, and you will see that when you make the way size positive, you will get y squared minus x squared minus z squared equals 1, which is our classic hyperboloid of two sheets formula that they give us. Okay, we are given r of t, and we're looking for curvature. So the equation that I like to use for curvature, I'm not really sure why, it seems to work best for me. I I like drawing increasingly crazy k's. I'm not sure really how you even get that symbol. But curvature, the way I like to find it is a of t cross v of t, magnitude of a of t cross v of t over magnitude of v of t cubed. This just seems to be the easiest one for me. If you can cross product things quickly, it's no problem at all. So we know that a of t and v of t are going to be our derivatives of r of t. And in fact, I'm going to move our equation over here so we have space. V of t is going to be just our derivative with respect to t of each of these components, which is 0, 10t, 4. And a of t is going to be 0, 10, 0. We also see that we're dealing with the curvature at 0, so we can replace this 10t with just 0 because we'll have 10 times 0 in here. So the, let's see, ooh, that's a cool k. Curvature at 0 is going to be the magnitude of v cross a. Well, let's figure that out. Crossing these two, we are going to get negative 40, 0, 0. So the magnitude of that is just going to be 40, and then we are dividing by the magnitude of v of t cubed. Well, the magnitude of v of t, let's see, magnitude of v, and it's really v of 0, is just 4, and that cubed is going to give us 64 over here. And we can simplify things down, and we will end up with 5 over 8. We have a particle with some acceleration and an initial velocity, and we're looking for the distance traveled from t between 0 and 3. We know that in the end, we're going to be solving the integral from 0 to 3 of v, of the magnitude of v of t dt. And this should be relatively easy to solve for. We can integrate each component of a of t to get v of t and adjust given our initial velocity. That integration is going to give us c1 t squared plus c2 and root 2t plus c3. And we see whenever they tell us initial velocity, that really means root t is equal to 0. So when t is equal to 0, we want our velocity vector, and I'll be specific here, this is v of t. We want our velocity vector to be 1, 0, 0, which means c1 has to be 1, c2 has to be 0, and c3 has to be 0. So now finding the magnitude, we'll be able to take our integral. So the magnitude of v of t is just going to be all of these components squared under one huge square root, which will be 1 plus t to the 4th plus 2t squared, which will factor down to the square root of, let's see, t squared plus 1 squared. Is that right? Let's make sure. Yep. Okay, that looks good. And so this is going to cancel out, and we'll be left with t squared plus 1. So now we can take the integral from 0 to 3 of t squared plus 1 dt, which is t cubed plus t, that over 3, from 0 to 3, which will give us 12. A traveling particle has a position vector given by that whole thing, and we're looking for its speed at t equals 1. So we know that speed is equal to the magnitude of v of t. And in order to find v of t, we need to take our derivative of r of t. So v of t Oh God, this is going to be a big one. I remember this question. Okay, we are going to get cosine of t minus t sine, that's a bad n, t sine t, and then sine t plus t cosine t, and then negative 2t. Okay, taking the magnitude of this is a bunch of fun because magnitude of v of t is going to be the square root. Here's where we need to break out the big square root. Cosine squared t, and I'm squaring these individually. So I'm squaring this guy first, this guy second, this not. There we go. That guy third. If you want to follow along, cosine squared t minus 2t sine t cosine t plus t squared sine squared t, and then we're adding sine squared t plus 2t cosine t sine t plus t squared cosine squared t plus 4t squared. Ah, God. But thankfully, almost all of this cancels out. V of t is equal to, I'm just going to copy this whole thing over. I don't feel like rewriting anything. We'll just cancel things out. This negative 2 sine t cosine t will cancel with this positive 2 sine t cosine t. Let's see, this cosine squared t and this sine squared t will turn into, will turn into 1. Go. And this t squared cosine squared t plus t squared sine squared t will just turn into t squared. So overall, everything is turning into 5t squared plus 1. There we go. And we're looking for its speed at t equals 1. Well, we can just plug in 1 for t and we get root 6. Okay, the level curves of this function right here are what? So we know that when we're looking for level curves, we just set our f of xy equal to some value k, and we kind of try to put this into a form that we will recognize. So k is equal to root x squared plus y squared plus 1 plus x. We can rearrange this to k minus x squared equals x squared plus y squared plus 1. This will be k squared minus 2kx plus x squared equals x squared plus y squared plus 1. We can get rid of this guy here, and we are left with something that we can hopefully identify. In fact, it'll make it easier if I move this. Oh, whoops, I'll just give up. There we go. And this isn't a form that we can identify, even if it's a little confusing. And if it helps you, you can kind of go through a process of elimination instead of just identifying it right off the bat. Looking at this thing, it's definitely not sometimes a line and sometimes an ellipse. We would need an x squared to get an ellipse anywhere in here. We would also need an x squared to get a circle. So it's none of those guys. We would also need an x squared to have a hyperbola. And instead, this whole thing is just a parabola. And I should have been clearer earlier. All we're doing when we set z equal to k over here is just pinning this 3D shape at some constant for z. So it's like you're taking a slice of your surface at some value z and seeing what 2D trace you're left with. Okay, question 8. We're taking this gnarly looking limit, which actually isn't that bad. I'm not going to rewrite all the limit notation outside of it, but we'll notice if we plug in 0, 0, bad things happen. So we're going to have to do something, because if we plug in 0, 0, we will end up with 0 over 0 equals 12, which is obviously no good. So we can't directly evaluate this. Instead, you might be able to see, we're going to have to do some factoring. So we can rewrite this limit, I almost said integrand, it's not an integrand, but you know what I mean, the expression in here as x to the fourth minus y to the fourth minus 3a x squared plus y squared over x squared plus y squared. And very nicely, this thing right here is going to factor to x squared minus y squared, x squared plus y squared. And now things get really nice because we can cancel out an x squared plus y squared term from everything, and we see that this is equal to 12, and we're still approaching x and y, we're approaching 0 with both x and y on our left side. So this whole little bit right here is equal to 0, and we're left with negative 3a is equal to 12, so a is equal to negative 4. The tangent plane to this thing at this point is, well, something. We got to find it, and it's intersecting the x-axis at some point, and we're finding that point. So we know that when we're given an explicitly defined surface here, our tangent plane is going to be in the form z minus z naught is, well, I shouldn't say fx, zx, x minus x naught plus zy, y minus y naught, where these naughts are just, in our case, going to be the point that we're taking the tangent point at, and our zx and zy are going to be our partial derivatives of z with respect to either x and y. So we can find those pretty easily. Zx is 2x plus y, and zy is x plus 4y, and we can't just put those in as they are. It'll be much easier if we evaluate them at this point that we're taking our tangent plane at. So this guy over here is just going to be 3, and here we get 5. So we can already start filling in some blanks. This thing is going to be 3. This thing is going to be 5, and we can actually fill in all our naughts too, because we already said all our naughts are just coming from this point right here. So z naught is 4, x naught and y naught are both 1. And we're very close now because if we evaluate this thing at this point here, we can replace all of our x's with a's, all of our z's and y's with zeros, and so we are left with something that we just have to do the algebra on to figure things out. And I'm just kind of working through it. A equals 4 thirds, and we're done. Okay, f is a differentiable function of x and y, and g is a differentiable function of u and v, where g is composed of u and v, and it's equal to f, which is composed of x and y, each of which are composed of u and v. So, pretty confusing story they have for us here. We can kind of rewrite this nicely as f is a function of x and y, where x is equal to this x term up here, so u plus 2v cubed plus 1, and y is e to the uv minus 1. And we are using the table below to figure out gv at negative 1, 0. Well, we know that g of u and v is just equal to this thing over here, so we can think of this in terms of f. It's very important to note that this negative 1 and 0 are values for u and v over here. We're going to need to see what this is equal to in terms of x and y in order to be able to solve anything at all. So when u is equal to negative 1 and v is equal to 0, x is going to be negative 1 cubed plus 1, so x is equal to 0, and y will be equal to e to the 0 minus 1, so y is equal to 0. And that's important because yes, okay, sorry, okay, perfect. Just checking my work in my head. We know that because we're dealing in terms of x and y over here, the point in the table that we actually care about is 0, 0. And they'll often do this where you'll be given coordinates that are either one level too high or one level too low in terms of the multi-dimensional function that's composed of other functions, and they'll just try to stick that in there. But that's almost never the correct point, because what they're trying to get you to do is realize that, okay, this is in terms of u and v. We need a point in terms of x and y to solve for any of this. And I'm kicking myself internally right now because I didn't mention at the beginning this is a multivariable chain rule question. They like to hide them. This is one of the more obvious ones. Whenever you see a table like this, it's a multivariable chain rule question. On the final that I took a couple weeks ago for fall 2019, the multivariable chain rule question that we had on there looked nothing like multivariable chain rule questions that we've had in the past, and it took a lot of thinking to actually realize what we were dealing with. But really, it was just recognizing that there was a function that was composed of another function, and they wanted a rate of change. So back to the present, we know that, let's see, that's not a g, that gv of -1, 0 is going to be equal to fx xv plus fy yv. And that's just from the definition or the formula for the multivariable chain rule. And we already have two of these values. Since we know that we're looking at the point x is equal to 0, y is equal to 0, fx is 5, and fy is 7, given there by the table. And so all we need to do is take the partial derivatives of x and y that we have over here with respect to v. So xv, we'll see that that is 6u plus 2v squared, whereas yv is going to be ue to the uv. And evaluating these at the same point, -1 for u and 0 for v, we see that this guy over here is equal to 6, and this guy over here is equal to -1. And we can plug these things in, times 6 and times -1, and we'll get our answer of 23. Let's find the directional derivative of this function at that point towards the direction of this point. So we know that our directional derivative is going to be made up of fx and fy. We need that vector, and then we need to dot it with the unit vector. And in fact, I won't even try to make up some notation for that. The unit vector of the direction that we are pointing in. So let's figure these things out. Fx from up here is going to be 2xy. Fy is going to be x squared plus 2yz. And we need some actual numbers for these. Well, we can just plug in our point 1, 2, 3. For fx, we will get 4. And over here, we will get 1 plus 12, so 13. And sorry, I just left something out. This is a function of a function of x, y, and z. We're dealing with a kind of four-dimensional function here, so we also need an fz, because I'll just add this in here. We're actually doing not x. What am I doing? We're doing this thing, and that should be a. There we go. Okay, we're dealing with a four-dimensional function here. So fz, we'll see that that is just equal to y squared, which is 4. So now we have this vector here, 4, 13, 4, and we are dotting that with the unit vector of the direction that we're pointing in. So that means we need a vector that points from 1, 2, 3 up to 3, 1, 5. And we'll see that that vector is 2, negative 1, 2. But we're not done yet because this is not a unit vector, so we need the magnitude of this, and we need to divide every term by that magnitude. Our magnitude is just going to be the square root of all these terms squared, which is the square root of 9, which is just going to be 3. So we can divide everything by 3 over there. And finally, computing everything out, we are going to get 8 minus 13 plus 8, which is 3, and that divided by 3 is going to give us 1. So there's our answer. Finally, let's classify these critical points, 2, 2, and negative 3, 0. And all we need to know for this is the rules for the second derivative test. This is essentially the easiest possible second derivative test question that they can that they can give you, because all you need to know are the rules that usually you'd have to bring in at the end of another question after doing all the math for yourself. There have been very, very mean ones, especially on the final. They like to get really, really rude with it. But we know that with the second derivative test, we're solving the matrix fxx, fxy, fyx, and fyy, mainly for its discriminant. We know that if the discriminant is greater than 0, that if fxx is greater than 0, the point that we have plugged in is a min, and if fxx is less than 0, the point is a max. We also know that if the discriminant is less than 0, no matter what, we're dealing with a saddle point, and if the discriminant is equal to 0, we know absolutely nothing. Okay, so looking up here, we know that the precondition for something being a critical point is that gx and gy, in this case, are both equal to 0. So we see that both of these points satisfy that, because gx and gy over here are both equal to 0, but they already told us that they were critical points up here, so I highly doubt they would try to pull that kind of trick on us. We can form the matrix for G at 2, 2. This is just going to be negative 2 for fxx, negative 2 for fxy, and negative 1 for both the other places. And it's important to remember that fyx and fxy, with all the functions that we're dealing with, will be equivalent. And that's a good way to go check your work. If you've computed fxy and fyx and they're not equal, something went wrong somewhere else along the line. So taking the discriminant of this, we're going to get 4 minus 1, which is 3. And since the discriminant is greater than 0 and fxx is less than 0, we are dealing with a local maximum at 2, 2. And finally, plugging in negative 3, 0, well, not plugging it in, setting up the matrix that they give us, we are going to get 0 for fxx, negative 6 for fxy, and negative 3 for these other positions, which is going to give us a negative discriminant, and so we are dealing with a saddle point, and A is our correct answer.